And today's speaker is going to be Arvind, and he's a creator of several instructional tutorials, such as websites from ev3lessons.com, primelessons.org, and flltutorials.com, which has been helping FLL teams since 2014, teaching them how to build and program Lego robots. He's from the Championship World Team in Festival in 2018, and today he's going to be talking to you about how to improve the reliability of your FLL robot using both mechanical and programming techniques. With that, I'll pass it off to Arvind to carry on with his presentation.
Hi, everyone, and thanks, Arman. As he said, I am going to be talking about ensuring the reliability of your First League Challenge robots. And then a little bit of background. Arman went over this as well already, but I've been competing in, or I've competed in First League for many years, and most notably, I've won the Champions Award at World Festival in my final year. So why focus on reliability? The main thing is that reliability is the #1 challenge that teams face. And this is because one, robots tend to work well at home, but not when they get to the competition. And two, robots tend to only complete missions sometimes and not other times. And the main effect of this is that teams tend to get frustrated. So these are the 5 issues that I've seen teams have that are common reliability issues. So 1, teams say that the robot does not drive straight. 2, it does not reach the same location every single time. 3, an attachment or motorized arm does not perform consistently. 4, also relating to attachments, or could be for the robot itself. If something moves too far, it could stall and the robot could get stuck. And then 5, the robot is crooked after line following. And throughout this presentation, I'm going to be going over a series of tips and tricks that your team can use to solve some of these common issues. And I'm going to start with trying to achieve reliability mechanically. So I found that every good First League robot should have this set of features that will help make it more reliable. So those 6 features are it being sturdy, it navigating well, being easy to repair, well-balanced, modular, and easy to code. And I'm going to go through each of these 6 features more in depth and how they can be used together. Let's start with the sturdy robot. So what I've seen from teams that I've helped their mentors is they need to learn how to build in a way that's going to ensure that parts of the robot aren't going to fall apart. And there's certain techniques that they can use to be able to strengthen some of their attachments or the robot. So to do this, to explain this, I'm going to show you a few examples of weak connections versus how a strong connection can be formed, achieving a similar goal. So let's take a look at the first example with the axles. So with the axles, you see 1 and 2. So 1 is basically axles that are smaller axles that are each connected through these yellow axle connectors. And 2 is just one long axle. And it turns out that the #1 is actually going to be stronger in this case because so #1 is going to be the stronger of the 2 because it's made up of shorter axles, and this is going to prevent twisting and bending of the axle. So with the case with the lift arms that's below it, you can tell that #2 is stronger because it's connected on both sides and with more pins than the other version. And with the third example on the right with the frames, I have 3 examples for this one because it's not always just about making something strong, but making something efficient as well and efficiently using parts. So this third example uses the idea of a crossbeam where two things are connected, and then you have a beam in the opposite direction that's holding them together. So you'd first have to take off that beam and then pull them apart. So a force pulling them apart wouldn't be able to take apart those two frames. And then the number 3 would actually be just as strong as number 2. However, it is a lot more inefficient in its use of parts, as well as heavier than number 2, which is why if I were deciding which one would be strongest and efficient, I would pick number 2. And the main rule of thumb that I follow is that you should at least have 2 points of connection on all of your parts, and try to use cross beams where you can. Okay, so let's take a look at how to make sure that your robot navigates well. So I find that a lot of teams, when they build their robots, they tend to have tires that bow outwards, and that's not good for your reliability. So I recommend that you have an outer wall on all of your robots to make sure that not only the entire robot is sturdy, but those wheels are being held in place from both sides and they won't bow. Also, having ball wheels in the back can also be useful for allowing for smooth turning. And then sensors. We're going to talk about this in the programming portion of the presentation a little bit later, but using sensors and placing them in the proper positions on your robot is going to be extremely important. And finally, I also recommend having wheels on the sides of your robot. And what that is going to do is allow for wall riding and also smoothly coming off of the wall. You can also use something like a bumper in the front or back of a robot that could be the same thing as your outer wall, that's going to allow you to back into a wall or mission model to align it to it. Okay, so the next thing is making sure it's easy to repair. And the first thing with that is with cables. So there's a few different ways that you can manage your cables. So one thing you can do is have colored clips or rubber bands or something to be able to know where you have your cables connected to between motors and sensors. Another important thing is to make sure that your cables are neatly tucked away and not near any of your moving components of the robot. You'll find teams that have robots that aren't moving straight, and some of the time it'll actually be because a wire is rubbing on a motor or rubbing on the wheel, causing it not to go straight. Another thing that's sometimes overlooked when building a robot is to make sure that you have all the ports that you need easily accessible. So your charging ports and download ports on the Spike Prime, they're the same thing, which is nice. But making sure those are accessible. And if you are using something like AA batteries on an EV3, then you should make sure that you can access those batteries or the place where the batteries come out. Just in general, make sure that your robot is very fixable at an event because anything could happen, it could break. You might need to disassemble to fix something inside. And another thing that I recommend is either taking detailed photos of your robot or creating a CAD drawing of your robot, which is going to help with repairs if you know where everything belongs, if something has fallen off. Okay. So well balanced. The other issue about when people say that their robot isn't driving straight is usually has to do with balancing the robot. So if you have an imbalanced robot from left to right, this can cause your robot not to drive straight. Just make sure it's balanced left to right, and then be extra careful when you're adding attachments that those attachments aren't adding excessive weight to one side of your robot. The other thing with balancing your robot well is with height, because if you have extremely tall robots or robots where the weight is high up, then they tend to be imbalanced and jerk when you're driving at high speeds and trying to stop. And that's not something that you want. So it's often helpful to have a robot that is modular or has a modular attachment system. And the idea with this is that you can have one base design and you don't have to redesign the robot for each mission, or physically add and take off different things manually. But if you have this nice system where you can add attachments that's modular, so an example on the right here is this gearing system where we have gears that are in the motors, and then we have a corresponding set of gears that are an attachment. So this attachment slots in and actually meshes with the gears to provide power to an attachment. And this is a lot easier to put in than, for example, like putting two pins together to connect your attachments. And this is sort of like this base attachment that you can add on to put arms and different things to add functionality for completing different missions. And there's all sorts of different ways for doing this. For example, you can directly put attachments into axles or axle connector slots, shown in the image on the left. In the middle, there you can have a system with gears and these pulley wheels that can mesh together, as well as the system on the right with pulley wheels with pins, axle pins, and pulley wheels without them that can mesh into each other. And each of these have their own drawbacks and their own advantages. So it's really up to your team to decide which system is going to be best for you. And I've personally used all 4 of these different systems that I've shown in this presentation in First Cycle League. Okay, so next is making sure that your robot is easy to code. And the main thing that I want to point out here is determining the size of your wheel. So larger wheels are going to make your robot drive faster, but they're going to be harder to control and less reliable. And smaller wheels are the opposite. They're slower, but they tend to be more reliable. The other thing is with rubber that can easily come off the rim or compresses a lot, which causes it to have a lot of variance depending on the weight of your robot, which can cause some can cause your robot to be unreliable. And then some wheels, like the Spike Prime wheels, can get dirty, and you have to wipe them. So it's important to try different wheels and figure out what's best for your team. And I've used all sorts of different ranges of wheels when competing in First Cycle League. So there is no best wheel that I would recommend, and they all have their own advantages and disadvantages. It's really up to you to try and test different wheels and figure out what's best for your robot. And the next important thing is to test your robot. So being able to check before you just go into programming missions, if it drives straight, if the wheels slip, if it's good at line following, can it do all the things you want to do, like align on walls, lines, mission models, and modify as you need and test again before just going into programming to make sure that your robot is how you want it and has the features that you want and works reliably. And then this is an example of putting all those features together. This is DroidBot C on ev3lessons.com, and it incorporates all of these features that I just discussed. The first thing you'll notice is this outer wall that goes all the way around the robot to keep the wheels supported. It also has those riding wheels I talked about to ride along walls. The outer wall also allows it to back into walls to straighten out. There's 2 color sensors that are separated, which allows for line squaring, which I'm going to talk about a little bit later. And they are well in front of the driving wheels, which is going to make line following more reliable. And then you'll also notice the very low center of gravity with the brick as low down as possible. And this is going to prevent things like the robot jerking, as well as the overall balance from left to right to make the robot go straight. It also has these 2 motors facing upwards that you could put any one of those different attachment meshing systems that I discussed, which provides an easy way to add attachments. Okay, So one thing that I haven't talked about yet is that you don't always have to have a motorized attachment. And sometimes passive attachments can be both easier and more reliable than a motorized one. And so the example on the right is from an old robot from my team in Nature's Fury. And it shows an example of pneumatics and rubber bands being used to help complete a lot more tasks than we could have just having the extra 2 motors that you're allowed. So this helped us complete a lot more missions and multitask and do things a lot more quickly than we could have just using our motors. And yeah, these are some different examples of passive attachments that are either gravity based. So these two are gravity based, and then rubber bands and pneumatics. So there's a lot of different ways that you can make passive attachments that are reliable. And then some other various strategies that might help you increase reliability. So one thing to note is that this robot in the image that you can see is from my team's robot in Food Factor. And we had this strategy where we wouldn't add any attachments on. And the entire time, only thing we would do, we'd have as much on as possible the entire time, and then only take off certain things. So you can take a look. If you just look up Droids Food Factor Run, you'll be able to find that online. But this is good because it will help you reduce your time that you spend in launch, and increases your reliability because there's less issues with putting things on and taking things off. And if everything's on there and already set, it could increase your reliability. And it's also, I personally think that it's great for rookies as a place to start instead of having complicated attachments that you take on and off, and to try and have something that you could keep on the whole time or take off as you go. Another important tool that my team tended to use a lot in First Lego League are this concept of aligners. So the idea here is you have these angled pieces. And what they do is that if your robot is slightly off when approaching a mission model, these aligners would align you to the correct spot to fit inside the mission model. And this significantly improves with the reliability because you can't expect your robot to be perfectly in the correct spot every single time. And these aligners allow for at least like 3 lift arm difference from left to right and still be able to work. And you can see an example here from our Nature's Fury run where we aligned up to the house to ensure that that worked every time. And then just some general robot design advice. One is that you can often score more points with a simple and reliable robot than a complicated one. So focus more on reliability than trying to do all sorts of different things, because that's really going to help you a lot. Next, you can start with a basic design, but be able to adapt it to what you need, and don't feel pressured to replicate what I'm calling the latest fad. So like the XYZ robot or box robots. One is that judges do recognize robot designs from the internet. So do cite your sources, and two, consider what features that you really need. Be able to look what features on that robot that are good, and then be able to incorporate that into your own. And then just a quick note on box robots. A lot of people think that it's something like special, and people even buy designs for box robots, but box robots are really just normal robots with a wall around them. So it's exactly what I was saying with the outer wall, but you just build upwards further and make it into a box. And so you can really convert any robot into a box robot. Okay, so before I move on to programming for reliability, are there any questions on the mechanical side of things that anyone wants to ask? And I can answer that.
I don't see any in the chat yet, but we'll give people a couple seconds to get those in. Couple I came up with is, could you probably maybe explain a little bit better of what wall riding is and what that's useful for?
Yeah, so wall riding essentially allows your robot to make sure that it's parallel to a wall. All you have to do is drive along a wall, and you can program it to curve a little bit to make sure that it stays along the wall. And the reason why you have wall riders instead of just a flat side is because depending on the table you're on, there could be like knots in the wood. It might not be as smooth. So having those wheels increases your reliability on different wall surfaces by making sure that you have a smooth connection along the wall. The second thing that it does is it makes your exit off of the wall a lot smoother, and it makes it easier for a robot to drive off of the wall if you have those wall riders.
Awesome. And it looks like we have a question about how do aligners work?
Okay. Okay. So aligners, I don't know if you can see my cursor, but there are these angled sections on the aligner. And what that does is when it hits the angled section, it's going to be pushed diagonally into, well, essentially your whole robot is being pushed left or right using these aligners. And so you will be a bit angled coming in, but when you drive into it, you're going to straighten up. So it's basically when you hit the angled part, it pushes the robot into place, into this little slot in the aligner.
Awesome. I think we have another question. Someone said I think they joined a little bit late, and they didn't get to see what the wall riders were. So they're requesting if we go back that slide really quickly.
Okay. So wall riders are, I think I'm going forward instead of backwards. My bad. Okay, so wall riders are just little wheels. Let's see. Okay, so here. So you just see these little, these are pulley wheels, but you can use any wheels you want. But basically just small wheels that are along the side of the robot. And that's just going to allow it to roll along the wall. And one thing with the aligners as well is if my explanation didn't make sense, they're really simple things to make. So if you just make one to the size of like a base of one of the mission models you have, you can try like pushing that, just like those two angle pieces in and seeing how they work for yourself. Okay, but yeah, these are the wall riders. Are there any other questions?
I think we're good for now.
Okay, I'm going to move on to the programming for reliability and just post any questions you have in the chat as we go along. Okay, so first, using sensors for a lot of teams might seem hard, and a lot of people are scared to try using them, but you're really going to save a lot of pain by using sensors because they're going to significantly increase your reliability, and you're not going to get as frustrated if your robot's working more reliably. So using sensors is extremely important. So the big challenge here is being able to navigate to a mission reliably. And if you take a look at any year's mat, but this one is an example of the Cargo Connect mat, there's lots of different places on the mat where there's potential to align your robot to a position so that it knows where it is on the field. So first thing you'll notice right away are these lines. So with lines, we could follow lines and we can also find lines. We can also align on lines as well. So those are the three things we can do with lines. And then there's walls as well as flat mission models. And with that, we can basically just drive into them. And it's going to allow us to square up or become perpendicular to that flat surface. As well as with walls, we can also ride along them. And then in addition to features on the field itself, you can also use the gyro sensor to ensure that your moves and turns are straight. And you should also repeat these techniques as often as you can. And if you see an experienced team robot, they will align a lot to be able, especially when they're trying to get across to the opposite end of the board. Being able to use these different techniques becomes really important. So let's start with finding lines. The main problem that teams have with finding lines tend to be in years where the mat has a colorful background. For example, this year does definitely have a colorful background. So the problem with colorful backgrounds is that the sensor, when you're looking for the line and driving along, it might see black sometime when it's driving, and that can be a problem when you're trying to find a line, because if it sees black, or if you're trying to find the white of the line, then white in this example, but if you're trying to find the line and it finds something earlier, it's going to stop in the wrong spot, and the robot's going to be very confused about where it is, because you think it should be on the line, but it's really not, because it stopped earlier. So the tip that I give with this is to first move pretty close to what you know is pretty close to the line, and then start looking for white. And that's going to significantly reduce the error, because you're driving over less of the background when trying to find the line. Okay, let's next take a look at following lines. So following lines, the main thing here is that you should make sure that you're actually on the line before you start line following, because if you're not on the line, it's going to have some trouble getting to the line and then line following. So some things that you can do here is first try to move until the line, that we know you're on the line. And then you could turn to become somewhat straight to the line. Of course, it's not going to be perfect, but if you can turn to be pretty close to straight to the line, that would be very good, because if you're line following already pretty straight, it's going to have a easier time line following. And then the third thing, which was one of the main issues that teams face that we mentioned at the beginning, was that if you are crooked after a line follower, you have to find another way to straighten out again. So for example, if there's an intersection, so let's say I'm line following on this bottom line on the mat, there's a perpendicular line at the end of it. So I could actually, after line following, square up to that line, and then I know I'm straight. I could also back into the wall on the south end of the field. That would also make me straight. The other thing that you could do is try smoother line follower, because basic ones tend to zigzag a lot or move back and forth. But if you learn how to do something like a proportional line follower, then that's going to significantly reduce that zigzag, and you're going to end up pretty straight at the end of your line following. Okay. So I've been mentioning aligning a line or squaring up to a line quite a few times in this presentation, but what exactly is it? So what it is if you have two color sensors, you can actually straighten out by driving until both color sensors see the line, and then stopping the corresponding wheel once that sensor sees the line. And you can use this to become straight, perpendicular to the line. As you can see in this image here, we start off angled. Once the top sensor sees the line, we stop the top wheel and then keep driving with the other wheel until the other wheel sees the line. And then that's how you get to the right image where it's straight. And you might actually have to do this multiple times to make sure that you're perfectly straight. And yep, so that's what I was saying here. You might have to do it multiple times. And this is just an example of the code would be like. So it's actually a pretty simple technique that you can employ in your code that's really going to help increase your reliability, because now you know that you're perfectly straight to the line. Okay, so the next thing is aligning on walls or emission models. So this one is pretty simple. All you really have to do is make sure you have a flat surface on your robot and then drive into it. And what that's going to do is when you drive into it, it's going to make sure that that flat portion of your robot is parallel to the wall or emission model. What's really important here is to make sure that when you're doing this, you're with a mission model, you're driving into a mission model that's both has a flat surface, but is also fixed to the ground. And that's the only way that you'd be able to do that with a mission model. And then the other important thing here is that when you're driving into a wall, you'll think your robot's just going to get stuck there because it doesn't complete its move. The wheels get stuck, which is why it's really important to use moving for seconds here, because that's going to prevent motor stalling. Because if you use degrees, it's going to hit the wall and it's not going to go its full degree amount. So make sure you use seconds, because that's just going to end after some number of seconds, no matter how far it got. And then wall following. I've mentioned this earlier as well, but using those wall riders, just driving into a wall and then making sure that you can also put a little bit of angle into the move with like the steering value for the movement block. You can actually set it to like 5 or something to actually curve into the wall, and that's going to make sure that you stay on the wall. And that makes sure that you're parallel to the wall. Okay, so some more on wall following. So now that you're on the wall and you want to get off, there's a certain procedure that you have to do to actually to get off the wall. So if you notice in the figures here, in figure 1, if I'm trying to curve off the wall with my wheels in the front, then the back of your robot's actually going to hit the wall and your robot's going to get stuck. In figure 2, we're fine, because if we're turning into the wall, then the back of our robot is going away from the wall. So there's not going to be a problem there. But to solve problem 1, there's 2 solutions. One is a programming solution. You can make sure you can make the robot curve off of the wall smoothly. So same idea with the different steering values. If you curve off smoothly instead of doing a sharp turn, you will be able to get off of the wall, but it'll take up a bit more space to do that. And then there's the building solution, which is the same thing as those wall riders I was talking about earlier, but having those small wheels make the connection with the wall more smooth, which will allow you to turn off of the wall more easily. Okay, next thing I wanted to talk about is how to use the gyro. So the gyro sensor, you can create a gyro move straight program, which you can find on ev3lessons.com or primelessons.org, a tutorial for how to do that if you're using Robot Inventor Spike Prime, or if you're using ev3, of course. And what this does is, even if your robot's bumped by something, or let's say you do have a lot of weight to one side of your robot, it's going to ensure that your robot goes straight by adding extra power to one wheel to basically curve and make sure that you stay on track with a certain gyro reading. For the EV3, it's important to note that you will have to learn how to calibrate your gyro sensor. And this is because of the issue with drift. If you shake your robot as you're turning it on, your sensor is going to calibrate and think that that moving value is actually still. And so you'll have to learn how to recalibrate it to teach it what still is. But there is a common misconception that you need to recalibrate before every time you turn. And this is not true, and you don't want to do this. Please just do it once when the brick is turned on, and that is it. And then if it starts drifting again, then you can do it. But really, it's just once when the brick is turned on, and you don't want to have any calibration programs inside your run. Okay, so another thing that we talked about was a common problem teams faced was with what's called motor stalling. And that's when you have a motor go for a certain number of degrees, but it gets stuck before that. And what's going to happen is it's just going to keep trying to go that certain number of degrees, and it's never going to make it. Example of this is, let's say you have a motor arm that's coming down over a mission model, but it hits that mission model 2 degrees before it finishes its move, and you want it to be right on top. It's going to just keep going, trying to get past and do those 2 degrees, but it's never going to make it. And so that's where stall detection comes in. You can stop the motor move and just move on to the next block in your programming if your motor happens to be stuck. And in Spike Prime and Robot Inventor, this is actually built in, which is really great. There's just a block where you can turn it on and off, and it will automatically do that for you. And in EV3, you can create code that checks the speed of the motor to tell whether it's stalling or not. And of course, if your speed is really low, then it's probably stalling. Okay. And you can learn more about that on Prime Lessons and ev3lessons.com as well. And then again, it's really important to test your robot often to make sure that your hardware and software are robust enough to work in different lighting conditions, different tables, if the mission models are placed differently. And so there's a few things that you can do here. So there's this worksheet that's on FLL tutorials where you can record different tests and if how often certain missions worked. And I recommend one, if you can, test out on a different table, because differences in tables can affect the way your robot moves, and you should be able to count for this when you go to competition. Two, you can just pick up, like, take your mission models off of the dual lock and just place them a little bit off, because they're not going to be exactly the same when you go to competition, and see if they still work then. And then also just run it a certain number of times, like run it 10 times and see if it works. And if it's not up to your standards, let's say you want it to work 8 out of 10 times or 9 out of 10 times, if it's not up to the standards that you have, how reliable you want it to be, then you should go back and revisit that mission and see if there's a different solution that might be more reliable than what you have now. Or if you can incorporate some of the features that I discussed in this presentation to help improve the reliability. And so this is just a short conclusion of each of those 5 problems and the different solutions that I discussed for how you can solve them. So the robot not driving straight, it's usually because it's either imbalanced, the wheel is not supported well, if it's bowing, if the tire is off the rim, that can cause it to not drive straight. And then one thing that I noted during the presentation was also if a wire is caught in the motor or the wheel. Okay, so number 2, the robot does not reach the same location each time. One, make sure that you're starting the same point in launch area every time, so you can use different markings. Or what I usually recommend is just starting against a wall, because that's a really easy place to know that you're always in the same spot. And then make sure that you use this reliability techniques of aligning on walls, mission models, line following, using aligners, so that even if you are a little bit off in launch area, it'll still work. So number 3, attachment does not perform consistently. One would be making sure that you build sturdy designs. Also start your attachment motors from the same point. Robot gets stuck on a mission model. That one is solved by the stall detection that I just discussed. And if the robot is crooked after line follower, I would recommend aligning in some way after it, or using a smoother line follower like a proportional line follower. So where can you learn more? FLL Tutorials has starter robots and lessons, engineering journal worksheets, and tools such as a sketch planner and a scorer. Programming with the EV3, you can learn from ev3lessons.com. And then similarly with Spike Prime or Robot Inventor, you can go to primelessons.org. And then for community support, if you have any questions, you can always make a post or join and make a post at FLL Share and Learn Facebook groups. Okay, well, that's the end of my presentation, and I'll check out some of the questions that people have in chat now and post, if you haven't already, you can post some questions in chat and I'll answer them.
Awesome. So we have one question asking when they should use stall detection. They're wondering if they should use it for every mission or only some missions.
So that's basically what we did on my team is we had it integrated into all of our moves, both for driving and for motorized attachments. So we basically use it for everything. I don't know if there might be some special cases where you wouldn't want it to stall, but usually you'd want it to stall in the hopes that it's gonna, even if you don't solve a particular mission, you could move on and then be able to continue on and still maybe score some other points, or at least make it back to home, so that you don't have to take a penalty for grabbing your robot. So I would use it as much as you can.
I have another question about how stalling works in general. I don't know how you want to interpret that, but I think they're wondering kind of what it is.
Okay, so stalling is essentially if you're running a motor for a certain number of degrees or rotations, and the motor gets stuck or hits something before it reaches that target number of degrees or rotations. And what's going to happen is, because it hasn't reached that target, it's just going to keep applying power until it reaches it, and it's just going to keep trying forever if it's stuck. And your robot's going to stall because it's not going to move on if it's still trying to complete that one motor move. And you're going to end up having to, if you don't have stall detection, you're going to end up having to grab your robot and take a penalty.
Awesome. And we'll wait for some of the questions. In the meantime, could you explain like kind of what a gyro sensor does? Like what does it actually, what information does it give you?
Right. So the gyro sensor tells us what angle the robot is at. So the Spike Prime actually has a 6-axis, well, 3 axes of gyro and then 3-axis accelerometer. I suspect the gyro will be more useful for teams probably. And generally you're going to want to use what they call the yaw angle, which is basically like the turning of your robot, and that actually does depend on your orientation of your hub. But if you have it oriented in the way as like the image shown here, then it's going to be yaw. But essentially, yes. So it's going to tell you your angle, and the way we use that to move straight is you have a target heading or a target angle. So let's say I want to stay at 0 degrees, because if I'm always at 0 degrees, then I know I'm going straight because I'm at that same angle the entire time. And so that's where the move straight comes in, where if I'm, let's say, going to 2 degrees, I need to curve off to the left to get back to 0. If I'm at -2 degrees, I need to curve off to the right to get back to 0. So it essentially tries to keep you at that target angle reading, and that's what's going to help you move more straight.
Yeah, perfect. And I think we have another question. I think people are still a little bit confused about the stall code. She might have missed the section of the presentation. She's wondering what code works to detect that stalling. And I believe you said there's a block for it as well, and there's also a solution. So maybe if we could go back to that slide.
Yeah. So with the Spike Prime and Robot Inventor, there is a block. It's in the motor block section, I believe, since it's blue, and it's built in. So if you turn this on, all of your motor blocks are going to automatically check for stall detection, then move on to the next block. So if you have an EV3, on the other hand, the code is fairly simple, but you can check out ev3lessons.com for exactly how to do it. But essentially the idea here is that you're going to start a motor running, and then you're going to continuously check what the power or what the speed of that motor is. And so if you think about it, like if the speed is reading 0, that means your motor isn't moving. And you can check like, so when it's supposed to be moving, as in like when your motor's running and on, if it is, and I wouldn't say equal to 0, I'd say like less than 2, because it might not read exactly 0. It could be like 1 power. So if it's less than like 5 or less than 4, less than 3 power, then you know that something's wrong. If it's supposed to be going at like 50 power, let's say. So if the speed is really low, then it's probably stalling. And what you can do is you can just exit the loop. and that's just going to stop it from moving and then move on to whatever's next in the code.
I think we'll take our last question here. We have a question about, can we do stall codes in Python? I don't know if that's applicable, but that was the question that was asked.
Yeah, stall detection is definitely something that you can do in the word block software as well as in the Python software.
I assume that that would require a custom solution rather than the.
Well, you can use for Spike Prom and Robot Inventor. You can do that in the MicroPython. And then with EV3, you would have to do that yourself.
Awesome. Are there any other questions? So it is 6:40. It's about 6:45 at this point. But are there any other questions before we conclude today's session? At this point, you can also unmute if you'd like to ask your question that way. Well, if not, then that was, I would like to thank Arvind for coming out today and teaching us about robot reliability. And if you'd like to look at the other sessions that are available, feel free to go to the main room for another session that's going to begin at 7 p.m.